Hello and welcome everybody, my name is Simon and today we will have a look at the Moon as a planetary environment for landing rover missions. The Moon is our nearest celestial body, so it seems quite logical that it is and also was one of the most desired targets for rover missions and also manned missions. As we all know, humans have been to the Moon several times in the 60s and 70s, and thus we have actual samples from the Moon as well as in situ images which will come in very handy for future missions. But before we get into the Moon specifics, we will have a short look on planetary rovers in general. So first of all, the primary goal of the rover is to navigate and traverse unknown and also hostile terrain while deploying scientific instrumentation for acquiring samples. And these samples can not only be images or videos, but also collecting rocks or drilling holes. There are some critical constraints for planetary rovers that typically don't apply for rovers that we use on Earth. First of all, we have adverse terrain with rocks and cliffs and also very few features for self-localization. Like you can imagine on the Moon, there's only gray dust everywhere. Also, we typically don't have any a priori data, which forces the rover to explore the environmental features by itself. This is especially necessary for navigating on another celestial body, which cannot be done by teleoperation because the time of flight of the signals is typically too large for driving a rover live on another planet. For the Moon, for example, the round trip time is around 3 seconds, which makes teleoperation just possible. But if you take another celestial body like Mars, for example, we have times of flight of at least 13 minutes, which means autonomy is a must for every other celestial body that we might want to explore. And all that has to be done in really hostile ambient conditions like thermal extremes and dusty environments like you have on the Moon, for example. We do also have limited power availability and high reliability requirements, which limit the mechanical complexity, as we cannot send a mechanic to space if something breaks, so we have to make the parts as simple as possible. On the right side you can see the Chinese Yutu-2 rover, which landed in January 2019 on the Moon, and it's actually the only rover on the Moon that is still active right to this date. Which directly leads us to the key features of the Moon. First, starting with gravity, that is, the gravity on the Moon is 1.62 meters per second squared, which is pretty low compared to the Earth's gravity. Also, the Moon is locked in a resonant orbital revolution around the Earth that equates the Moon's axial spin. That means that we can only see the same side of the Moon from Earth. And also, this results in a 29 Earth day long synodic day for the Moon, which means we have a 2-week day and 2-week night cycle, and therefore extreme temperature differences between the day and the night. At the equator we have around 120 to 380 Kelvin, which equates to minus 150 degrees Celsius to 100 degrees Celsius. But the temperatures can get even colder and can be as low as 40 kelvins on the poles, which would equate a temperature of minus 230 Celsius. The Moon has no atmosphere and has a solid core, which means there cannot be any global magnetic field on the Moon. And the surface of the Moon is heavily scarred by impact basins and craters and is characterized by the so-called rugged highlands, which represent the older crust, and the younger, smooth, so-called Maria plains, which are the darker spots on the Moon. Also, the surface of the Moon got pulverized to fine-grained regolith by microtektite bombardment. That means very small, like centimeter big meteorites pulverized the surface of the moon over time to fine moon dust, which we call regolith. And regolith, as well as other rocks and minerals that you can find on the moon, are all solid, and there are only 4 minerals that make up 98% of the lunar crust. And also there are no water-containing minerals such as, for example, clay, which we may find on Earth. Which leads us to the decade-old question of, is there actually water on the moon? Clearly, if there's no water in form of clay, maybe water is liquid, or is there actually water ice on the surface? Let's find out. First of all, there cannot be any liquid water on the moon, as the liquid water would get vaporized and also decomposed by the sun's radiation, and then would be lost to outer space. But what about water ice? So it has been suggested that water ice may reside at the bottom of some craters on the moon. And it turns out there are some craters on the poles that are deep enough or have enough difference in elevation that, combined with the low solar inclination angles at the poles, there exist some areas on the moon that never get direct sunlight and therefore are really cold. Cold enough, in fact, to trap ice over long periods of time. In 2008, NASA sent an imaging spectrometer called Moon Mineralogy Mapper, or short M3, to Moon. The instrument was mounted on a satellite, and the mission's goal was to create the first mineral map of the entire lunar surface. Then in 2009, water was detected on the moon by the detection of water characteristic absorption features, which then were confirmed in 2018 by a more detailed analysis of this data. Okay, let's have a look at the actual data. On the left side, we can see our 4 reflectance spectra ranging from 1 to 2.5 micrometer wavelength in the infrared spectrum. And at the bottom in blue, we have the spectrum of pure water ice. You can see that water ice absorbs infrared light in the wavelength 1.3, 1.5 and 2 micrometers. And for comparison, the top spectrum in black shows a pixel without any ice in it. And between it and the blue one, we can take a look at 3 different locations on the moon in red, where you can see the drops in reflectance values at the water characteristic absorption lines. Then on the right side, you can see the north and south pole of the moon and where the corresponding locations are. Each dot in these images corresponds to 1 pixel of M3, which is around 280 by 280 meters big. If you are like me and wonder how we can measure any reflected light from permanently shaded crater regions, actually, the measurements are only from shadowed areas where indirect illumination is present. For example, reflected sunlight from nearby topography. Of course, then the material that reflects the sunlight does also have a specific spectrum, which then in return influences the measured spectrum in the dark regions. That's why the actual spectra have to be calculated by taking the spectrum of sunlight as well as the spectrum of the material into account that scatters the light into the shaded regions. As we can observe, we have water ice in the polar regions and also potentially other volatiles that come from cometary impacts or are solar implanted. One example for a solar wind implanted gas is helium-3, which is very rare on Earth, and its occurrence on the moon is thought to be greater than here on Earth. Therefore, the moon would be our closest source for helium-3, which theoretically could be used for clean nuclear fusion in the future. But back to confirmed evidence of water on the moon, which could be really useful for future manned missions, as it can not only be used for drinking water, but also can be used for fuel generation, to be used in fuel cells, for example. Which leads us to the choice of a potential landing site for future missions. Let's say our mission goal is to find and sample water ice in the crater regions with a planetary rover. Then we have several requirements that need to be fulfilled. First of all, we need good illumination to generate solar power, which we obviously need to operate our rover. Then the rover needs good view to Earth for us to communicate with the rover. If this is not the case, we could potentially also use some kind of communication satellite in the moon's orbit or relay stations on the surface. Of course, we also need a feasible route into the crater regions where we want to conduct our search. And also accessibility for orbital imaging and ideally a rock-free and relatively flat terrain. As an example, we can have a look at the right, where we have a height map of the south pole of the moon. And in some polar regions, especially on the mountains, we have line of sight and also good illumination. So let's zoom in a little bit on the South Pole and take a look at the Shackleton crater, which is 20 kilometers in diameter and 3 kilometers deep. If you have a look at the right map, we can see that there are places on the rim of the crater which are near all year illuminated, which is of course favorable for energy generation. However, the Shackleton crater is a relatively young crater. This means that the sides of the crater are much steeper. Thus, a traditionally six-wheeled rover may not have enough traction, and a tracked rover may be better suited for this environment. If you have a look on the map, you can see several potential landing sites that lie in the sunlit parts, and also some routes that the rover could potentially drive to get into the crater. However, it's incredibly complex to plan a route in this environment because we do not only have the unknown properties of the terrain, but also another impeding property of the moon, which we need to take into account, and that are shadows. In fact, on the poles of the moon we have extremely fast moving shadows which can cause instant changes between light and dark, which is not only challenging for energy management but also imposes rapid temperature changes on the equipment. So we need to put a really good heat management in place for our rover to survive this environment. When talking about environmental conditions, we cannot ignore another challenge we need to address when designing a rover for the moon, and that is lunar dust. The moon's soil is made up of fine dust that has the pretty annoying property that it sticks to everything. If we take a look at the lunar dust under a scanning electron microscope, it becomes clear why. On the left side we have one grain of lunar dust which has sharp and jagged edges all over the place, which results in a lot of surface area and also places where it can catch to other things. In comparison, if we take a look at the right image, we have dune sand from the Sahara Desert. We can see that the grains are smooth and round, without any sharp edges. That is because of the constant movement and abrasion by wind, which we obviously don't have on the moon because of a missing atmosphere. As a side note, this is also the reason why Sahara sand cannot be used to make concrete, because of its particular round shapes. To make matters worse, the unshielded solar UV radiation is so strong that it kicks out electrons of the upper layer of the regolith, which makes the dust particles effectively positively charged. They now act like broken up styrofoam balls that cling to everything, and if the particles are small enough, this electrostatic charge is even sufficient to make the dust levitate above the surface. We can see the frictional and electrostatic properties of the lunar soil on the images from the Apollo missions, where the spacesuit and the equipment is completely covered in dust. And if we now think of our planetary rover, dust is not only bad for every mechanical component like gears, joints or bearings, but also reduces the effectiveness of solar arrays if they are covered in dust. So when designing a lunar rover, we have to come up with some strategy to get rid of the dust or to protect mechanical parts from coming in contact with it. There are multiple different approaches to accomplish this. One of them is vibromechanical, essentially shaking or vibrating parts to shake the dust buildup off. Another method is electromagnetic dust removal, which only works if the dust has magnetic properties. The best working method for lunar dust, however, is electrostatic dust removal. This works by applying a voltage to several parallel electrodes lying next to each other. The trick is to delay the voltage for every electrode in such a way that it is out of phase with its neighboring electrodes, which creates a fast-moving electromagnetic wave that transports the particles away. This works quite well, as you can see in the video. Most of the dust is gone instantly when turning the device on. If you want to use this technique on solar panels, for example, it is also possible to make the electrodes transparent by using indium titanium oxide semiconductors. Quite recently actually, there was another technology proposed which uses an electron beam to clean the surfaces from dust, which you can see in slow motion in this clip of their experiment. For motors and moving parts, we often need some kind of bearing to remove the friction in combination with some fluid or dry lubricants. All these places where moving parts meet each other are potential ingress points for dust, which then creates wear on the parts or in the worst case could seize them. For planetary rovers, we therefore need special seals that can withstand the pressure and temperature environments in which they operate in. Teflon, for example, is a material that works for these extreme conditions like we have on the moon, and therefore is used as a material to make the seals out of. In these images you can see how such a spring-loaded Teflon seal looks like, and the testing jig that was used to test these seals for 10,000 cycles, while being exposed to lunar simulant material. This material has actually similar properties to the real lunar dust. In this particular test, the researchers observed minimal wear on the part, but most importantly, none of the simulant material could make it past the seal. Another interesting solution are so-called magnetic fluid rotary seals. These are seals where the sealant is a ferromagnetic fluid that gets held in place by magnets, and therefore cannot leak out into space. But let's get back to rovers on the moon. For that we want to take a look at the next big rover mission to the moon, NASA's VIPER mission. VIPER stands for Volatile Investigation Polar Exploration Rover. As the name suggests, the objective of this mission is to land the rover on the south pole of the moon and characterize the distribution and physical state of water ice and also other resources that the rover may find on its way. The researchers want to understand where they come from, as well as finding out if in situ utilization of these resources could be possible for future missions. Using water, for example, is a huge game changer, as water is heavy and expensive to bring to space. Water can obviously be used for drinking water on manned missions, but also can be split up in hydrogen and oxygen, which then could be used to breathe and also to be used in fuel cells for generating power or even as a propellant for rocket engines. The VIPER rover measures about 2.5 meters by 1.5 meter and is 1.5 meters tall, so comparable to a golf cart in size. It has solar panels and batteries for power generation, which can supply up to 450 watts of peak power. Because of the low solar inclination angle, it makes most sense to put the solar panels on the sides of the rover, which looks pretty unique compared to other rovers that we might have seen before. The driving speed of the rover will be around 0.4 to 0.7 kilometers per hour, and operation is done by semi-automatic teleoperation. So there will be operators here on Earth that will tell the rover where to move for the next few meters and then get near real-time feedback and also video data in return. This data gets sent directly back to Earth via the X-band radio, without the need of a relay station. And for the rover to be able to see in the dark, VIPER is actually the first rover to be equipped with headlights. Amongst the video cameras and headlights, the rover is equipped with 4 main instruments. The first one is the NSS, which is a neutron spectrometer that points down and can detect water in up to 1 meter depth below the surface. This is done by analyzing the number and energy of neutrons that come from the moon. If these neutrons collide with hydrogen atoms, they lose energy, which then can be measured. And as water consists of hydrogen and oxygen atoms, the neutron spectrometer is a pretty good tool for detecting water below the surface. In this way, the rover can map the presence and amount of water in the soil while driving. This helps us to determine places where to drill into the ground, which brings us directly to the next instrument, which is called Trident, short for the Regolith and Ice Drill for exploring new terrains. This drill can drill about 1 meter into the ground and also measure the temperature along the way. The drill has a carbide tip that is harder than steel and therefore lasts much longer. Also, the drill can operate in so-called rotary and percussion mode that can be controlled independently from each other. When retracting the drill, a rotary brush sweeps off the material into a chute, which then creates a small pile on the ground. This pile can then be analyzed with the NIRVIS instrument, which stands for Near Infrared Volatile Spectrometer System. As we have heard before, water ice can be detected by analyzing the absorption spectrum in the infrared wavelength. This is exactly what NIRVIS is doing, as well as characterizing other types of minerals or ices that may be in there. The big tube you can see on the left of the instrument is an infrared lamp that shines light onto the surface, while the smaller black tube are the optics for the infrared sensor, which are actually from Schneider Kreuznach from Germany, as I'm just noticing right now. But apart from that, the last instrument on the rover is the mass spectrometer observing lunar operations, or short MSOLO. It is essentially a modified off-the-shelf mass spectrometer that can analyze gases in the environment. And it can also be used to create a signature of the gases that come from the lander upon impact, so that researchers later can distinguish what comes from the moon and what gases may originate from the lander. Also, the mass spectrometer can detect materials that may evaporate after the drilling when they're having a bit warmer temperature. You have probably seen that the Viper rover will have a 4-wheeled chassis for driving on the moon. As explained previously, the moon's soil is inherently dusty and a wheeled vehicle could easily get stuck in these conditions. For that, the Viper rover has its 4 wheels mounted on articulated legs that can help to get the rover unstuck and allow several alternative driving techniques besides normal driving. Now let's have a look at the video from the testing facility where we can see these alternative locomotion modes and see how the rover is driving in quicksand-like conditions.
The goal of the test here at the Slope Lab is to test the latest Viper mobility prototype in this facility in order to verify requirements. That means we want to check that the system does what it is supposed to do once on the moon. The Viper test unit that is behind me is a light version of the full Viper rover. We strip down the heavy components to try to maintain the mass load so that we can drive on Earth, which has a much higher gravity. And we need to do this because the system is designed to go to the moon where it will be a lot lighter.
We have consulted NASA scientists who have analyzed images and data from previous Apollo missions to determine the distribution of rocks and craters of different sizes over certain areas of the terrain and the shapes and characteristics of rocks that we expect to see on the surface. So what we've done is use that information to recreate a moon-like terrain for the rover.
We're testing our rover capabilities when we go into an extreme sinkage environment. So on the moon, when we're roving, we might encounter areas with fluffier soil, something similar to quicksand. And so our rover has a capability to still make forward progress in these quicksands. We're also testing the ability that the rover has to move in a very special way. It's similar to a caterpillar inchworming motion. So the rover is able to change the distance between its wheels and apply power to the wheels in a very coordinated manner, and that would allow the Viper rover to get unstuck of this quicksand.
This is challenging for the rover, but it's important to test because we need to better understand and mitigate risks and hazards to the rover. And we have a great team of NASA engineers here to address any risks that we might face.
When finally on the moon, the Viper rover will be operated 24/7 in 8-hour shifts. The driving is done step by step on a waypoint basis. Every waypoint is chosen by the operators based on what they can see on the images from the hazard cameras of the rover. In this way they can build hazard maps to find a safe course to drive for reaching the next waypoint. The main goal is to find the clearest path, avoiding big rocks or any potential obstacles where the rover could get stuck. The driving routes will be around 2 weeks long. Then the rover must reach a safe haven where it can park to survive the times where radio contact is not possible. This is because the moon has some amount of wobble, which is called libration, that makes the pole shift out of the Earth view for about 2 weeks. During these periods, the rover should have solar power to keep the internal components heated, as the rover can only survive 50 hours in complete darkness. And for the software people out there, lots of the rover's flight and ground-based software is made up of open source projects. To visualize the data received by the rover, the web-based Open Mission Control Technologies software, which you can see in the screenshot, will be used. OpenMCT was developed by NASA and has already been used on several other missions in the past. But also some key components in Viper's operating system will be adapted from the Robot Operating System, or short ROS2, that people working with mobile robots might be very familiar with. And with that, I'm coming to an end for this video. I'm curious what Viper will find out. Until then, we will have to wait until next year, where Viper is supposed to launch, and hopefully gather lots of new data and insights on its 20-kilometer long roving endeavors in the permanently dark regions of the moon. I really hope you learned something about how to bring mobile rovers to the moon. This is it from my side. Have a great day and goodbye.